right, first and foremost, thank you everybody for taking time out of your busy schedule to come here for our senior design presentation. My name is Alfred, Salas. My colleagues are Daniel Oliva, Pedro, Cuberos, and our advisor is Dr. Andres Tremonte, and our senior design is a 2016 FIU SAE Powertrain Optimization Package. What is FSAE? FSAE is an international collegiate competition which is hosted by the Society of Automotive Engineers and allows participating engineering students to apply their engineering skills gained in the classroom to design an open-wheeled styled race car following strict FSAE rules, regulations, as well as global standards. FIU Panther Motorsports is broken down into 7 categories: powertrain, chassis, drivetrain, aerodynamics, ergonomics, business marketing and e-board, and electrical electronics. Within these categories, they break down further into subcategories. For example, our powertrain breaks down into the intake system, exhaust system, engine components, gear train, as well as the drivetrain. Due to the infancy of the FIU team, we typically only have about 20 active members, which equates to about roughly 3 members per category. So this is a previous design of the intake and exhaust and powertrain system of the 2015 chassis. For the current design that we were going to work on, we were going to incorporate an intake plenum. Furthermore, we're going to relocate the intake away from the exhaust. This way we can reduce the heat radiation from the exhaust to allow for a denser air charge for better fuel atomization as well as overall performance. Another aspect we're going to look at is 3D printed material as well as a tuned exhaust and an overall weight reduction of the vehicle. So first thing when you do is when you're doing an optimization, you have to first determine your powertrain. The powertrain that we are using is a 2009 Yamaha YFZ 450 engine. It's a single cylinder, dual overhead cam, 4-stroke. And before you do any kind of intake design, you have to determine your base CFM airflow. The way that you do this is use this calculation over here. You get engine size, which is cubic inch diameter, which is 27.4 times engine RPM divided by a conversion factor of 3456 times the volumetric efficiency. Since this engine is a high-performance engine produced by Yamaha, the volumetric efficiency was estimated to be 90%. So what we did here is a CFM versus RPM graph. Since the CFM requirement is directly related to the engine RPM, we broke down 3 lines, 90%, 85, and 80. Since the max RPM, running RPM of this engine is roughly 10,000 RPM, that equates to about 71 CFM. So during a 4-stroke engine, you have intake, compression, power, and exhaust. Intake is the only time in which the intake valve is open, and during this duration, the piston is moving downward in the cylinder, and this pressure differential allows for the atmospheric pressure to generate the velocity profile within the intake. One of the issues that we do have in internal combustion engines is the remaining of the 3 strokes, compression, power, and exhaust, the intake valve is closed. What this causes is a disruption in the velocity profile coming in the intake, and as the air bounces off the valve, it creates a compression wave. The reason that we're doing the intake plenum is to reduce or mitigate the effects of the compression waves, as well as optimizing it by choosing a different material as well as something even smoother on the inside.
Hello everyone, my name is Daniel Oliva, and I'm going to be talking about the overall design process of our intake manifold. So to begin, Alfred and myself have both done internships in General Motors, and we wanted to follow a design process that was similar to what is used in industry, particularly with the automotive industry. So with that in mind, we decided to go with first designing our iterations in CAD using SolidWorks provided by our university, and then doing the CAE work in both ANSYS Fluent and Ricardo Wave engine simulation software. In ANSYS, we can obviously do a Cfd analysis and get an idea of the flow within our intake. And with Ricardo Wave engine simulation software, we can build a 1D model of our engine and do quick comparisons between different iterations to see what our gains are in terms of horsepower and torque for the overall engine. Finally, the last step would be taking it to a chassis dyno and to validate our results by measuring our output at the dyno. Unfortunately, due to an engine failure in our car late in the game, we had to order a new stator and our motor, and that put back our deadline, so we weren't able to finish that by today, but we will do that by our competition, which is on May 11th. So to begin with our CAD model, we want to take into account our design constraints from SAE and the rulebook. The first one being the competition requires you to have a 20 millimeter restrictor, as Alfred mentioned, that obviously restricts your horsepower and affects the intake design shape. The second one would be the surface envelope, which we had to take into account. This means that if you draw a straight line from the top of the roll hoop to the back of the rear tire, all your engine intake components had to remain under that line, so that obviously affects the overall shape of the intake. With our first design alternative, we were looking for two different things. We wanted to reduce the overall curvature of our intake to try to maintain a more symmetric flow, and we wanted to have the most unobstructed air going into the throttle. So with this in mind, our first design was to try to place the throttle body as high as possible. This design also utilized a rammed air scoop, which would gather the air above the driver's head and redirect it into the throttle. Unfortunately, this design made it difficult to stay under that side profile, so we had to go to our next design iteration, which featured the throttle body next to the driver's head. Now the cons with this, after doing simulation, was that the air coming into the throttle was very obstructed and wasn't the most optimum choice. So we went with our final design, which featured the throttle body on the outer edge of the roll hoop, and it also allowed us to point the throttle directly into the incoming flow and create a curvature that was smoother than the other two designs. Lastly, we looked at the cross-sectional area of our intake manifolds. After speaking with industry professional Ariel Vidal, who is a FIU FSAE alumni working in the powertrain department at Chrysler, he advised us to go with a more elliptical shape, which we later confirmed that his advice was correct through CFD in order to maintain a more symmetrical flow than a circular cross-sectional shape, which would produce pockets of vacuum within your intake. Next, we moved into the Ricardo wave portion. As I mentioned before, this software allows us to do quick comparisons between different intakes in terms of your overall horsepower and torque gains. The first step was to use a Ricardo wave measure program, which allowed us to convert our CAD files to STL and then mesh it so that we could input it into our model. The next step was also trying to increase the overall accuracy of our model and making sure that it's true to what we're actually running on our car. So what we did in order to ensure that was to measure the valve lift profiles of both the intake and the exhaust. So with this apparatus, we were able to bolt a cam degree wheel to the crankshaft and zero it out at top dead center, and at different angles along the crank, we were able to measure the displacement of the valve using a displacement gauge, as shown in the figure above. These were the results that we gained. So these are the measured values from 0 to 720 degrees. As Alfred mentioned, one cycle is 2 full rotations of the crank. So you can see where the intake valve begins to open, what is the max displacement, and also if we have any overlap between our intake and our exhaust valves. Lastly, this was the overall model that we built for our engine, and our final horsepower and torque figures that were made on our last iteration was 40 horsepower and 38.25 newton meters of torque. Now Alfred will go over the CFD process.
So we haven't mentioned, but we went through 100 intake iterations, and during this time, during the CFD analysis, instead of us theoretically coming up with calculations to input as our parameters for the CFD, we experimentally obtained them. One of the most important ones that we obtained was the intake air temperature within the intake manifold. So what we did is, the previous intake, there was an injector housing, and what we got was a K-type thermocouple, and we began taking recordings of the intake air at room temperature at initial startup, and once the vehicle reached operating temperature, we reached the max of 100 degrees Fahrenheit, and that was the value that we used for the temperature. Another thing that should be noted is that our final iteration, we had the throttle body perfectly horizontal, and since our maximum performance is to be obtained during the dynamic testing, the average speed that SAE states that the vehicles are on a track is around 40 miles per hour. So what we did is we then input the inlet velocity at 17.8 meters per second, which equates to 40 miles per hour. So that's another parameter that was extremely important, was the outlet pressure of the intake. Another way that we did that is we used a standalone computer, the PE3, and we ran and made recordings of the MAP sensor, the manifold absolute pressure. As the engine RPM increases, you can see that the pressure decreases, obviously because the intake valve opening and creating that pressure differential. So the value we used for that was 5 psi, which was the lowest rating that we got on here. So one of the biggest obstacles that we had as well was the CFD analysis. One of the most important features in CFD is the mesh. Pretty much what the mesh is an amount of nodes that you use for each simulation. The more nodes you use, the more time it requires, but the more accurate and the more detailed your results are. Due to the lack of the computing power that we had, as well as the lack of support from FIU, we had to use our personal laptops, and what we did was an initial fine mesh versus medium mesh, and we determined that the medium meshes could be used for all of the iterations, and then we would run a final mesh to verify that the information obtained in the medium mesh matched the final mesh. So before doing any of the CFD analysis, we used Ricardo wave to determine what characteristics to look for. We didn't just walk into CFD results and be, okay, hey, look, let's look for highest velocity. What we did is we went back, took a step back, went back into Ricardo wave, and started running intakes to see what was producing the most horsepower. What we found was that the ellipse shape, as well as large plenum volume, produced the most horsepower. And the reason for that, as you can see in the fine mesh, this is our intake, the final intake we made, intake iteration 110. As you can see, it has the most symmetric airflow, and there's 2 pockets in this region here, which allows for the air to continue coming in as the intake valve is closed. And as previously mentioned, we gained in the simulation 40 horsepower and 38 foot-pounds of torque, which is a 14 horsepower increase from the initial intake.
Good afternoon, my name is Pedro. I'm going to talk about the project management and cost analysis of the project. In order to successfully achieve our deadlines, we decided to use a software called Smalltalk. This software allowed us not only to map all the milestones required for the project, but also to keep track on the progress of each one of the individual tasks. As you might see on the slide, the first and second stage were completed, and we are just waiting on the dyno run and on-track test to complete all the tasks related with the third stage. We now translate this information into a Gantt chart where we were able to add more detail to each one of these tasks, as the responsible, the start date, end date, and duration in days. I'm going to talk about the cost analysis of the intake system. The initial cost of 3D printing both the intake plenum and the injector housing was initially $3,339. Nevertheless, the supplier of this service, of the 3D printing service, which is a company called Realize Inc., gave us a 75% of discount, which ended up in a total cost of $834.75. On the other hand, for the exhaust system, we initially evaluated the possibility of manufacturing customized exhaust for our engine. The total cost of this project was supposed to be $316.91, but then we received an offer from a company called Yoshimura Inc., which was offering a high-end carbon fiber exhaust system. This exhaust system not only complied with the noise regulations of the competition, but also showed to be 5 pounds lighter than the original exhaust. That takes us to a total cost of, for both the intake system and exhaust system of $1,124.74. I'm going to leave you now with that.
So to conclude our presentation, keeping in line with our design goals, Formula SAE is about following standards. It's not just about building a race car and a group of mechanics just putting things together. Formula SAE really pushes you to try to comply with rules and regulation, which are very similar to what you are going to be seeing in the automotive industry. These rules are relevant because a lot of these regulations are developed not only for the American market, but for both the European and Asian markets, which also has an effect on the rules that we're following. And to back that up, also the research that we did with the powertrain studies, this goes further into increasing the volumetric efficiency of our intake, trying to get the most power with the least amount of fuel and with the least amount of air. So due with all the research that we did and with our final analysis, we can say that we successfully were able to increase the performance of our engine. And with the following slide, you can see a video of our car run. First plan. So at this moment, we'd like to open up the floor for any questions.
Did you do any kind of full bench testing of the actual intake and exhaust off the engine?
I'm sorry?
Actual flow bench testing?
No, unfortunately, we tried to do a flow bench on our here at the university, and we found like an older dyno, but it wasn't up to a running condition, so we weren't able to get that data on the bench. As mentioned before, we're planning on taking it to a chassis dyno to measure what the final horsepower and torque gains are, including drivetrain losses and everything.
Typically, what a lot of teams do is they'll do modifications to the intake or the exhaust, do a flow bench test, and do simulation
Right.
on the software side.
The only reason why we didn't do anything like that is because, like I said, due to the infancy of the FIU organization and SAE, we only have one engine.
Right.
So for us to take the cylinder head apart and allow some of the students to try to modify it, we're running a risk of allowing them to do that, destroy the engine, and then we have nothing at all.
Right.
So when we do get a second engine, that's one of the things that we're going to be doing for future work. I'm going to be staying over here over the summer, so what we're going to do is hopefully we get a second engine. I'm going to be changing the cylinder head gasket to increase the compression, probably intake and exhaust porting to allow for higher CFM. And then we're going to go further with the tuning, and then maybe even try colder plugs and different scenarios to try to increase the power of the system.
Well, before you do the actual porting in the head itself, model it, create a mold, copy the design of the actual build of it, and pour resin to make a resin model of it, and use that to test several models. And practice running your porting and polishing of that. We actually do it on the actual engine. I've done some reading on that. It's really mess up some of that.
Oh, you definitely can.
By hitting the wrong area, but it's a science to that.
Yep.
The reason I was asking, now, as far as you said you did some kind of calculation. When you go to competition, take those hand calculations or your data, your spreadsheets, and take them with you, because the judges are gonna wanna see that. Now, you did the cost analysis. I guess I'll just retake whatever. The judges who do the cost analysis of the competition are typical engineers or Ford class. That's all they do. You know, they know it. That's what they want you to do, the cost analysis report, time design report. And they want you to send the cost design report way ahead of time so they can go through it. You know, most of these binders like this, but each book, each sheet, and they go through everything. Let's say somebody donated you an engine. Here you go, here's an engine. You better put it in your design report, the engine costs so much, you do the technical, so you got it.
Yeah.
I know teams who say, oh, I got that engine this thing, so I need to put in a cost report. He says, well, most of the other teams pay so many dollars for that engine, so we put that to the top of your cost. You know, so it's tough. Yeah, but once this is done, I want to give you guys my email. I have some ideas that you guys like during the summer and get ready for next week.
Yeah, that'd be great, actually. Charles, do you have any comments?
Good job.
Huh?
Thank you very much.
Thanks.